What is random and what is not? Randomness in cryptography is very important, from the formation of the key to the final output of the encrypted elements. Randomness is important at all stages. So, what is randomness in cryptography? Let's for example imagine an infinite binary sequence. I said infinite. A little bit more. Okay, enough. So, which of these sequences can be considered random if they are only 0 and 1? Traditional probability theory does not answer this question, it only describes the properties of a set of such sequences. So, if the probability theory states something about the properties of a random sequence, it means that the property is performed for the vast majority of sequences. Well, it's difficult, but it will become clearer. There are several approaches to the concept of randomness of an infinite sequence: frequency, complexity, and quantitative. Now, let's talk a little about each. The frequency approach, or as it also called the Richard von Mises approach, is based on the fact that in a random sequence there must be a stability of frequencies. For example, our 0 and 1 must meet independently and equal probabilities not only in the main sequence, but in any of its sequences. This sequence can be allocated according to any rule, without considering the sequence itself. Simply put, there are no regularities in a random sequence. In this case, the definition of randomness depends on the rule for selecting the specified sequences from the original sequence. But this definition has its drawbacks. Then, if we take a random segment consisting of units, we can consider this sequence as random. But is that really the case? According to the complexity approach, a random sequence should have a complex structure that cannot be described using a short text. So according to Shannon entropy, where the entropy of the system X is the sum with the opposite sign of all relative frequencies of occurrence of the state or event, with number I multiplied by the binary logarithms. In this formula, P is a set of probabilities of the considered complete event scheme, and according to this definition, implicitly assumes that the best algorithms for predicting the next symbol of the sequence is him guessing. And in this definition comes a slight contradiction. A finite segment of an infinite random sequence does not allow a simple description. So, how to be? The quantitative approach of prior-Martin law is based precisely on the fact that there are many random sequences, but not random sequences are rare. Not random are those sequences in which there is a consistent pattern, that is, any verifiable property of sequences inherent only to a narrow class. The sequences is random if it withstands tests that reveal such patterns. However, if you require a sequence to withstand any test, it turns out that there are no random sequences at all. In this regard, until we come up with nothing better than to limit the number of tests. For these tests, the proportion of sequences satisfying them should tend to 0, with increasing the length of the sequence. If you think which of these approaches is correct, don't worry. Between these approaches, there is certain relationship. So, the sequence is considered as random by complex approach in case when it's random with quantitative approach. The definition of randomness based on the frequency approach using different rules is broader, but even they strictly include sequences that are random in complex and quantitative approach. It's a little brain explosion, but don't worry, you just need to know that choosing your date of birth as a password is a bad idea. Cryptanalysts use those methods of mathematics that give them the opportunity to track patterns in the ciphertext. So, in cryptography, have come up with use random or pseudo-random numbers generator. They allow you to form a set of elements that corresponds to the definition of randomness. It's quite expensive to use random number generator. That's why, in our computers and smartphones, we use pseudo-random number generator. Let's look at an example how it works. Let this function computable in polynomial time, where g is our algorithm, n is the key length, and q is the polynomial. This function is called the generator. The source of entropy is very important for the generator. In simple words, the entropy is the measure of disorder. A pseudo-random generator uses a single initial value, from which its pseudo-randomness follows, while a random generator forms a random number having at the beginning a high-quality random variable provided by various entropy sources. Therefore, there are pseudo-random generators that have and do not have security proof. It's important to have on hand a cryptographically secure pseudo-random number generator. This generator has only two requirements. Must withstand the next bit test. The meaning of the test is as follows. There should be no polynomial algorithm which, knowing the first k bits of a random sequence, can predict k plus 1 bit with a probability of more than 50%. And the second one must remain reliable even in the case when part of all of its conditions have become known or have been correctly calculated. This means that it should not be possible to obtain a random sequence created by the generator prior to obtaining this knowledge by the cryptanalyst. In addition, if additional entropy is used during operation, an attempt to use knowledge of the input data must be computationally impossible. But in practice, it's not so easy, and most of the pseudo-random number generators are not suitable for use as an cryptographically secure pseudo-random number generator by both criteria. First of all, many pseudo-random number generators produce a sequence that is random in terms of a variety of statistical tests. They are not reliable in relation to reverse engineering. Also, some specially tuned tests can be detected, which will show that random numbers obtained from their pseudo-random number generators are not really random. Second, for most pseudo-random number generators, it's possible to compute the entire pseudo-random sequence if their state is compromised, allowing the cryptanalyst to access not only future messages, but all previous ones. Cryptographically secure pseudo-random number generators are developed with the consideration of resistance to various types of cryptanalysis. But stop worrying about everything. Most people don't protect their information at all. Let's take a little look at the Yarrow algorithm, which consists of four independent parts. The entropy accumulator collects samples from sources of entropy and places them in two pools. The receipt mechanism periodically complicates the generator key using entropy from pools. Generation mechanism generates pseudo-random number generator outputs from the key. And the receipt control determines the execution time of the complication. The entropy accumulation is a process by which the pseudo-random number generator receives a new, unpredictable internal state. In this algorithm, entropy is accumulated in two pools, fast and slow. In this context, a pool is a storage of initialized and ready-to-use bits. A fast pool provides frequent key receipt. This ensures that the discredit of the key has a short duration. Slow pool provides a rare but significant receipt of the key. This is necessary to ensure that a safe complication is obtained even in cases where entropy estimates are highly overstated. Input samples are sent alternately to fast and slow pools. The receipt mechanism connects the entropy accumulator to the generation mechanism. When the receipt control determines that the complication is necessary, the receipt mechanism, using information from one or two pools, updates the key that is used by the generation mechanism. Thus, if an attacker does not know the current key or pools, the key will be unknown to him after the complication. It may also require a large amount of resources to minimize the success of the attack by getting the input values. To generate a new key, the receipt from the fast pool uses the current key and the hashes of all the inputs from the fast pool since the last receipt of the key. Once this is done, the entropy estimates for the fast pool will be reset to 0. The complication from the slow pool uses the current key and the hashes of the inputs of the fast and slow pools. After the new key is generated, the entropy estimates for both pools are reset to 0. The generation mechanism gives the output sequence of pseudo-random numbers. It must be such that an attacker who does not know the generator key could not distinguish it from a random sequence of bits. The generation mechanism should have the following properties: resistance to cryptographic attacks, performance, or in another word, efficiency, ability to generate a very long sequence of signals without complication, resistance to backtracking attacks after the key has been compromised. In order to choose the time to receipt, the receipt control mechanism must take into account various factors. For example, too frequent key changes make iterative guessing attack more likely. Too slow, on the contrary, gives more information to the attacker who compromised the key. Therefore, the control mechanism should be able to find a middle ground between these two conditions. As samples are received in each pool, the entropy estimates for each sources are stored. As soon as this estimate for any source reaches the limit value, a complication from the fast pool occurs. In most systems, this happens many times per hour. A complication from a slow pool occurs when the estimates for any of the sources in the slow pool exceeds the threshold. In year 160, this limit is 100 bits for the fast pool and 160 bits for the slow pool. By default, at least two different sources in a slow pool must be greater than 160 bits to receive from the slow pool. Here's what it looks like. Well, now let's go ahead and consider what you cannot do without. Yes, it's series of number. Here it will be difficult and you will have to work very hard, because this part of cryptography requires a lot of effort from you. But I will tell you briefly some aspects which may help you to understand it. In computer processing, information is presented as sets of 0 and 1, binary sets. Each such set is assigned a natural number, the record of which in the binary notation coincides with this set. Thus, the computer processing of information is reduced to the processing of natural numbers. In modern cryptography, messages are represented by some finite alphabet characters, or sequences of such characters. These characters are assigned numbers from 0 to n-1, where n is the number of elements, power of the alphabet. Therefore, the encryption and decryption of messages are the transformation of natural numbers smaller than n. The direction of mathematics, the subject area of which natural numbers, is the theory of numbers. Thus, modern cryptography is associated with the use of the results of number theory, which has a long history of development. In view of the finiteness of the alphabets of messages, an important role in the section of number theory plays the congruence relation, in which the number having the same remainder of the division into a fixed number module are considered as compatible with the structure. For example, if 13 modulo 4 is equal to 1 and 5 modulo 4 is equal to 1, then we can say that the number 13 and 5 is congruent to modulo 4. As a model, it's natural to choose the power of the alphabet of messages. In traditional cryptography, with simple transformations, there was no need to apply deep results of number theory. The situation has changed with the advent of public key cryptosystems, which are based on unilateral transformations, such as the operation of exponentation by huge modules. The encryption conversion argument is an open message, and the function is an encrypted message. But first, we should consider how to work with the numbers. Under the numbers, unless otherwise specified, we mean an integer that is a natural number, positive integer, 0, and a natural number with a minus sign, or negative integer. The sum, difference, and product of two integers are also integers. The quotient of two integers, where the divisor is not a 0, can be either integer or non-integer. If the quotient from division a to b is an integer, denoting it by c, we get a is equal b multiplied c. In this case, it's said that a divides by b, or b divides a. The next thing you need to learn is the modular arithmetic. Consider the classification of integers by their residues from division by a given positive number m, which is called a module. The numbers having the same remainder belong to the same class and are called congruence modulo m. The congruence of numbers a and b modulo m is written as follows. The congruence of numbers a and b modulo m is equivalent to the possibility of representing a is equal b plus m multiplied t, where t is an integer. Before I explain to you what the fields are, I will remind you once again about simpler concepts in mathematics, sets and relations. The set is understood as an unordered set of different elements. In addition to the well-known operations of union and intersection of sets, we consider the direct or say Cartesian product of sets. The Cartesian product of A multiplied B of sets A and B is defined as the set of all ordered pairs x and y, such that x is an element of A and y is an element of B. This definition is written as follows. Through absolute value A denote the number of elements, the power of a finite set A. It's easy to verify that for finite sets there is an equality, absolute value A multiplied B, which equal to absolute value A dot product absolute value B. The relation between sets A and B is a subset of the Cartesian product A multiplied B. In the case B is equal to A, this relation is called the relation on the set A. But how does the notation work? The numbers in the mathematical disciplines called the symbols participating in the record of numbers. The number means its value. Note that usually when working with the computer you enter the numeral, not the numbers themselves. The purpose of creating any numeral system is to develop the most convenient way of writing numbers, in particular for simple and quick problem solving. For easy to use, the numeral system must have the following properties. Easy way to record a number on a physical medium. Convenience of performing arithmetic operations. Simplicity of learning the basics of working with numbers. But how the distribution of prime numbers exactly work? First, let us consider the distribution of primes in the natural series. Recall that there is infinity of prime numbers. In addition, the following statement is true. For any arbitrarily large natural number k in the natural series, there are k consecutive composite numbers. Let's consider these k consecutive numbers. It's easy to check that the I number of this sequence, where I is greater or equal to 1 and less or equal to k, is divisible by I plus 1. So, all these numbers are composite. The next thing I'll tell you is what is the greatest common divisor of several integers, a number that is divided of the data numbers without a remainder. The largest of the divisor is called the greatest common divisor, or GCD. The form of a GCD is A and B is equal to C, where C is a GCD of numbers A and B. For example, for numbers 10 and 16, the GCD is 2. 1 is neither a prime nor a composite number, because otherwise it will not be possible to prove the basic theorem of arithmetic. Naturally, prime numbers are 2 or more integers, the greatest common divisor of which is equal to 1, such that A and B is equal to 1. While for any non-negative numbers A in the power m and B in the power n, it's true that it equal to 1. If you want to find the GCD, then you should decompose the number into prime factors, with subsequent finding of the product of identical factors. The process of decomposition of numbers into prime factors often takes too much time. However, for a pair of integers, you can use Euclid's algorithm, which can be represented as this one. Let a and b be integers, and b is greater than 0. We reuse the divisibility property as this one. So, our a is 390 and b is 170. It's very simple. For example, a equal b multiply q sub 1 plus r sub 2, where r sub 2 is less than b, but it's greater or equal to 0. Q sub I is the quotient, and R sub I is the remainder of the division. Residues of R sub 2 and R sub 3, they are constantly decreasing, so they must eventually become 0. Obviously, A in B is equal to R sub n, because in reality R sub n divided by R sub n minus 1. Hence, the GCD of A and B is the last non-zero remainder in the above process repeated division. Hence, the greatest common divisor of A and B is equal 10. Note that this was obtained without factorization of any numbers. To date, Euclid's algorithm, despite more than 2000 years of history, remains the most effective algorithm known. This is only a small part of all the operations that are required to encrypt and decrypt your data. All modern cryptography is based on the experience that has been accumulated by mankind for more than 3000 years. And to understand this, you have to spend a little time. But don't worry. Now, to encrypt something, you just need to use ready-made tools and libraries. the developer must simply understand the principle of the algorithm. Later, we will look at how it works, but for now, let's find out what is the rings, groups, and fields. In mathematics, a group is a set for which we have defined a binary operation called addition and denoted by the plus symbol. For the set G to be a group, the addition must be defined in such a way that it corresponds to the following four properties. First, its closure. If A and B are in G, then A plus B is also in G. Second, associativity. Parenthesis A plus B plus C is equal to A plus parenthesis B plus C. Third, its identity. There is a single element 0 such that A plus 0 is equal to 0 plus A, and it's equal to A. It's similar to exclusive OR operation. And the last one is invertibility. Each element has an inverse value, that is, for each A, there is such B that A plus B is equal to 0. If we add the fifth requirement, commutativity, which means that A plus B is equal to B plus A, that group is called the abelian group. In the usual addition record, the set of integers z is a group. Moreover, it's an abelian group. The set of positive integers n, however, is not a group because it does not satisfy the first property. Groups are convenient because if we prove compliance with all four properties, we'll automatically get some other properties, as addition. For example, a single element is unique. Moreover, the inverse values are unique. It means that for every A, there is a single B such that A plus B is equal to 0. Also, we can write B is equal to minus A. Directly or indirectly, this and other properties of groups will be very useful to us in the future. In the group definition, the operation multiplication is not concretized. The group operation can be addition, for example, the addition of integers. If the operation is called addition, then the group is additive, and in this case, the unit element is called 0. And instead of the inverse element, a to the minus 1 power, the opposite element is used minus a. The additive abelian group is called the module. Multiplication of the same element by itself is written as an exponent. A subgroup is a group that is a subset of another group. A cyclic subgroup is a subgroup whose elements are repeated cyclically. A ring is a set of R with addition and multiplication operations, such that R is an abelian group with respect to addition and multiplication, and is associative and distributive with respect to the addition operation. As you can see, parenthesis A multiply B multiply C is equal to A multiply parenthesis B multiply C. A multiply parenthesis B plus C is equal to A multiply B plus A multiply C. And the last one, parenthesis B plus C multiply A is equal to B multiply A plus C multiply A. The result of the determination of the ring is the property that for any A where A multiplied to 0 is equal to 0 multiplied to A, and it's equal to 0. Examples of rings could be sets of integers, rational and real numbers with addition and multiplication operations. The ring in which this equation is equal to 0 implies that A is equal to 0 or B is equal to 0, and it's called the integral domain. If the ring has a multiplicative unit, then a ring is called a ring with a unit. Element A of rings with a unit such that A multiply A prime is equal to 1 and is called the inverse of element A. The element opposite to the element A of the ring is denoted by A to the minus 1 power. Each element of the ring has no more than one element to return to it. There is no element inverse to the zero element of the ring. The set of elements of the ring having the inverse element is in the multiplicative group of the ring R, which is denoted like this one. So, what is the field? The field is the ring F with unit, the set of non-zero elements, which with the multiplication operation is an abelian group. This group is called the multiplicative group of the field. Examples of infinite fields are the fields Q of rational, R of real, and C of complex numbers. A subset F of the field Q, closed with respect to both operations and being a field, is called a subfield. A field that does not have a subfield, that does not coincide with the field itself, is called a simple field. There is a single simple infinite field. This is the field of Q rational numbers. Finite fields are called Galois fields. The order of the field is the number of elements. The finite field of order Q is denoted by GFQ. For example, the simplest field is the field of two elements, the GF2. The operations of this field are defined by tables, from which it follows that the addition corresponds to the Boolean addition function by modulo 2, and the multiplication to the conjunction. It's through these processes that we can transform the elements of plain text into elements of ciphertext. All cryptographic processes inside your computer looks like this. The computer doesn't understand algorithms. It doesn't understand even random numbers. It only understands the logic that was said. The capabilities of the cipher sets its algorithms, and the reliability of the result depends on the mathematical justification, the reliability of which confirms the degree of cipher protection. It's really a complex science, but all these processes in principle are reduced only to this. So, don't be afraid to look into the theoretical part of cryptography if you want to understand in more detail how it works, at the essence you have already seen. In the next video, we will look at how cryptographic systems work.